Well, good morning or good afternoon. We're going to go over the gas law notes, at least for Boyle's law and Charles's law, named after a couple of British and French scientists that worked out some information with gases. So first off, part A is going to be properties of gases. And can you see that? Okay, properties, okay, I'll write better, of gases. There's only one S in the middle. Don't want to. So as we talked about when we did the reading on this, and I think just about everybody had mentioned this, gases can be compressed. Compressible. Oh, I-B-L-E, excuse me. Now that means they can be squeezed. In case you weren't sure of that term. And that's because gas particles tend to be far apart, and there's room in between them that they can be squeezed in a little bit closer. Cannot see that. Thank you for letting me know. There we go. Unlike solids, or even liquids, solids and liquids are very close to each other, the atoms. There is no room for them to be able to be squeezed any closer. And I'm going to have you mess around with the syringes in a little bit where they kind of show that property. Number 2, gases have very low densities. Now here's a weird thing. Gases are fluids. They are fluids, F-L-U-I-D. I'm going to rewrite that. They are fluids. A fluid in science is defined as anything that can flow from one place to another, from high pressure to low, and take the shape of its container. The main thing is they're just really low density fluids. We tend to think of fluids as water, which water is a liquid, but gases are also fluids. Okay, they take the shape of their container. So that's one of the properties of a fluid, is that they'll take the shape of whatever container you put them in. And number 4, they exert a pressure in all directions. Oh, and let's make that an equal pressure in all directions. So they exert an equal pressure in all directions. So if we had a balloon here, this is a balloon. Okay, balloon. The reason that balloons take their shape is because they are pushing outward on this. They're trying to escape out, but they're exerting a pressure in all directions on each other. And that's going to push the balloon to try to take the biggest shape it can take. So those are the properties of gases. You can squeeze them. They're low density. They're not heavy. They take the shape of their containers. They exert a pressure. Part B. I've been requested to move this down, and I will do so. Part B. This is going to be kinetic theory. Kinetic means motion or moving. And this is really simple. Kinetic theory says matter is made of moving. Matter is made of moving particles. Okay, instead of particles, let's say moving atoms or molecules. There we go. Hot expands. guess I should say heat. Heat, hot, expands matter. Cooling, cold, shrinks. Thank you for that. So, really good example, like sidewalks. They tend to have built into them cracks. And a lot of times you'll notice a lot of sidewalks, they'll even have a little piece of material, almost like a piece of wood or something in between. That gives room in summertime when it's hot and this expands. It gives a little bit of room for that to squeeze in there. Bridges, you don't need to draw this one if you don't want to, but metal bridges, they will tend to have, as you drive onto them, little zigzag grates. Oh, let me redo that, make it a little bit easier. They'll have, the bridge is connected together with little zigzags. I'd say don't draw this, that could just confuse. I got a better picture I'll show you later. But it's made so that these metal plates can expand into each other when it's hot in summer. Then in wintertime when they cool, they kind of pull apart, but they're still kind of held in place, and it keeps the bridges from totally breaking. Okay, I think we're just about done. Okay. Pressure. I know you're starting to feel the pressure now. Have you ever driven up in the mountains and you start to feel pressure on your ears? Your ears start to push in, or a bag of potato chips that's unopened begins to puff open. We can see pressure changes. So we're going to go units of pressure. Gases exert a pressure on stuff, so let's see. Units of pressure. We have 1 atmosphere. Do you know what the atmospheric pressure is right now on you? Make a guess. How many atmospheres is it? All right, 1 atmosphere. Now, we are having a storm right now, currently. It's raining outside, so it might be slightly lower. So 1 atmosphere. We're going to abbreviate this 1 ATM, not automatic teller machine, but 1 atmosphere. So this is the average pressure at sea level. AVERAG, average pressure. I'm going to abbreviate pressure, just PR for now. Average pressure at sea level when it's not raining on a day where there's not a storm at 70 degrees. Let's see. Okay. Now, there's other terms for this. So let's put 1 ATM is also equal to another unit. What am I going to do? 760 torr. Now, this is named after an Italian scientist named Torricelli. So this tends to be one of the metric system units. They'll use 760 torr, which is also the same as 101.3 kilopascals. Oh, so let's do kilo pascals. Chances are, if you ever have a bicycle pump, you're going to look on the, oh, I should have one here, I don't have it. When you look on the little dial as you're filling it up, maybe you're going to fill up a ball or your bicycle tire. You usually want to fill it up like to 32 psi, pounds per square inch, but you're probably going to see another little unit scale on there that says KPA. That's the metric version. It's kilopascals. Kilopascals. What else do we have? Okay, let's see. Okay, also, this is also equal to, I ran out of room over here. We continue it there if you have room. 760 millimeters of mercury. So you're going to see these units of pressure when we're doing these. We might say it's 1 atmosphere, or it's 760 torr, or it's 200 kilopascals, or 3,000 millimeters of mercury. But all of these are interrelated to each other, and you may need to make a conversion factor for those. Let's see, we're almost done here for now.
Mr. Kenny,
Yes.
so is it more equivalent to millimeters of mercury?
That is correct. The question is, are torrs equivalent to millimeters of mercury? That is correct. When Torricelli did his work along with Galileo Galilei on figuring out pressure, they decided to honor Mr. Torricelli's work by calling millimeters of mercury a torr in his name. So they're the same thing. And part D, Boyle's Law. Mr. Boyle's Law deals with volume and pressure. I'm going to write it out mathematically. P1 times V1 is equal to pressure 2 times volume 2. So you guys back there that are talking in the group, you need to know that when we say this pressure 1, that means the starting pressure or volume, and we have the subscript 1. When we have the subscript 2, that means the new or the final pressures. So let's see. I'll look at, what do you want to put, new or final pressures? Okay, we can say this is the new pressure and volume. New pressure or volume. Starting pressure or volume. And as we did in our lab, we found out that this is a inversely proportional relationship. Inverse, I-N-V-E-R-S-L-Y, inversely proportional. That means if pressure increases, then volume decreases. And you saw that as you added more books, you increased the pressure on that cylinder. You saw that the volume in that little tube got smaller. They're inversely proportional. And I think, you know, we're gonna do Charles's law. So I'm gonna have to flip the page. We're gonna go to C because I want to get those on there. Excuse me, E. Almost done. Then I'm gonna do some practice. Charles's law. Now, Charles's law deals with volume and temperature. Oh, appropriate. Okay, volume and temperature. Boyle's law was volume and pressure. Charles' law is dealing with temperature and volume. So his equation is the starting volume divided by the starting temperature is equal to the new volume divided by the new temperature. If you ever get a balloon and blow it up, and then you just let the air out, and you fill the balloon, it feels cold. Because as the volume is getting smaller, it affects the temperature. So that's, well, okay, so this is the relationship there. Now, what we're going to find on this one is this is directly proportional. Directly proportional. Proportional. Okay, spell proportional, Mr. Kinney. Proportional. There we go. Which means if you increase volume, what should happen to the temperature? If they're directly proportional, if we increase volume, what's going to happen to temperature? It would mean that it would also increase. with the example of the balloon I just gave you, when you blow up a balloon, it's got a large volume. When you let the volume get smaller, the temperature also gets smaller. It gets colder. Okay, let's see. Oh, yeah. Got to deal with something here. Temperature in Kelvin. We're almost done with the notes. I appreciate your focus here. Temperature in Kelvin. We cannot use degrees Celsius. Kelvin, which is K, is equal to the degrees Celsius that we give you plus 273. So anytime in any problems with Charles's law, when we tell you the temperature, if it's in degrees Celsius, you need to add 273 degrees to it, because these gas laws were based using a different temperature scale. I guess we could say in kelvins. They don't call them degrees Kelvin, they just call them kelvins. And let's see. So I'm going to stop there. Thank you for your attention. Okay, stop. Hello? No, I'm still going.